Okay, done. It worked, so let me see if the length is still correct. Length, sorry. Sorry again. Sorry, I made a mistake in the fourth cycle because I need to put an I in vector. So let me redefine the vector again. And then again the fourth cycle. You see that the check is always a good idea. Okay, now I make again a check of the length. It seems fine. Let me also make a check on the mean value, which should be unchanged. Yeah, it's unchanged. If I make the mean over the matrix and the mean over the resulting vector of averages, of course the average of the average should be the same as the average of the whole numbers. Okay, and let me just check also the maximum to see if there are no mistakes, and the minimum should be okay. These are millimeters per hour, by the way, I forgot to tell you. Okay, it's better not to plot now because we still have too many data. Okay, and I will make a plot once that we got the annual data. They are only 100 values, then we can start making plots. Okay, so basically now we have a vector which is range 2, which contains the mean area precipitation over the catchment. And now we have to start with our exercise. And the exercise, let's start with by fixing as duration the year. Let's work with the annual data. So now we have a good question because we have to aggregate these 876,000 numbers to get the annual values, annual rainfall, which is only 100. And of course it is conceptually very simple. We have to get the first 24 times 365 numbers, 8,760, and sum them. And then the second block taking the sum, the third block taking the sum. This is conceptually very simple, but of course if you think of the algorithm, you realize that it's not as simple because we need a fourth cycle in principle. But we have indeed actually an R function that helps us a lot. And the R function is called apply. I will show you how it works. And the first thing that we need to do to apply this function is to create a second vector which contains the index 1 for all the data of the first year, the index 2 for all the data in the second year, and so forth. Okay? So let's create this. So now the problem is how to create this vector. And I think the solution would be basically, let me just guess a name for the vector, like PR is equal to, I think the solution, the best solution would be a sequence of repetitions, but the problem is that the repetition should be carried out first on the number 1 and then the number 2 I'm trying to understand what is the best solution for doing that. So probably the best solution is, let me create first of all a sequence from 1 to 8, from 1 to a repetition first. A repetition 1, 8, 7, 6, 0. I think a 4 cycle is the best solution, so let me see. Let's try a 4. First of all, let's define the vector. PR1 equals 0. And then let's take a 4 cycle. 4I in 100. And then let me open a parenthesis because I'm not sure if I can stay in only one line. And it is to be repeated 100 times because we have 100 years. So I think that now the best solution is to do like that. Here 1 is equal to C, here 1, and repetition I 8760. I think this is the solution. Basically what I do is at each step to increase the vector PR1, to extend it with the number I, which is varying from 1 to 100, which is repeated 8,760 times. I think this should work. The only problem is, in doing this, you see that I have a 0 at the beginning, which should be removed. Because I needed to define the vector, and otherwise the 4 cycle would get an error. And therefore, to define the vector, I just put a 0 at the beginning. And then, for each I, what it does is, as I said, to extend PR1 by adding the number I repeated for the number of times that we wish. And therefore we get 8,761s, 8,762s, and etc., which is what we want. The only problem is that we have to remove the 0 at the beginning. So in order to do that, let me do this. PR1 is equal to PR1 2 length PR1. And then let's see if the length is correct. Yeah, it's correct. Should be fine. We may try to make a plot to see what happens. There are still a lot of data, but maybe that we can succeed in getting it. Yeah, it's fine. You see, we got this nice stair from 0 to, from 1 actually, to 100, which is what we wanted to get. So the sequence of instructions, again, here they are. Maybe there is a fasted solution, maybe that you can find it. I couldn't find quickly a solution to avoid the 4 cycle, because the 4 cycle is always something that we should avoid if we want to maximize efficiency. Because in this case it took like 1 second, so it's not significant. But when we manage a lot of data, you know, the cycles usually take a lot of time. And as I said, maybe that there is a fastest solution to do that, but okay, in this case I prefer, given that we need also, we don't have much time, I prefer to do that. Okay. And then a very simple application of the apply function. So let me write rain3 is equal to apply rain2 PR1 sum. So, what I did here is to apply a function, which is the sum over rain 2, and what should I sum? Should I sum all the elements of rain 2, which have the same value, corresponding values, in PR1. So basically the function summed all the elements in rain 2, which are associated to the index 1 in PR1. And then the sum of all the elements with the index 2, etc. And so I aggregated the data. And is this correct? First of all, let's compute the sum of rain 3, and let's check if it is the same value of the sum of rain 2. Yes, it seems correct. And the length of rain 3 should be 100. Correct? And now let me make a plot of rain 3, type equal line, to see if it is reasonable. Yeah, it is, indeed. The average rainfall that I am expecting over the catchment is, because there is a part of mountains, is something that in the flat area here, because this catchment is close to Bologna, in the flat area we have about 1100. In this case there are mountains. Let me see the average, mean, rain 3. Yeah, it's fine. So it is, everything is reasonable. So what is really interesting here is this function apply. In the same way as I apply the sum, you can apply the average, you can apply whatever function. It's a way to extract subvectors from a vector. And keep in mind that you don't need that the indexes are in blocks like here. Here I have PR1 where the indexes are placed in blocks. So it's first one, and then a block of 2, and then a block of 3. This is not necessary. You could mix these indexes and apply, looks at PR1 and gets all the indexes that have equal values, whatever they are displaced, and applies the function sum to the corresponding elements of rain 2. So it's very useful. Because also for computing the seasonal component, you understand that it's very useful. Because you may assign to each data an index from 1 to 365, and then compute the average over all the data collected on the 1st of January, 2nd of January, etc. It's very useful. Okay. And then we have this 100 data, and we have to compute the SPI. Once that we understood how to do it for the yearly data, you recognize that it's straightforward to do the same operations for monthly data, weekly data, etc. Okay, in this case, we got these annual values. And you remember that the first operation that we have to make is to bring the data to the Gaussian distribution. Let's see if the distribution is already close to Gaussian, because these are, you know, annual values. Maybe that we are already close to Gaussian. If there is something that you don't understand in what I'm doing, please stop me. The distribution indeed is quite nice. It's not really Gaussian. You see that it's not symmetric, but still, it's not far from Gaussian. So basically, we could also decide to assume that the data are Gaussian, but given that in general they are not, let me instead assume that they are not Gaussian. So let me explain to you a very easy way of transforming whatever bunch of data to the Gaussian distribution. Okay, so just 1 second that I don't remember by memory the function. So let me just have a look at my codes. And I should look at 1 second because I need to get back. Not here. So okay, here I am. Just 1 second. Let me make an attempt. So okay, so let me try this way. Okay, it should be this. Just 1 second. Okay. Okay, I'm ready. Just 1 second. I close the door. Okay, so a very simple R function to transform whatever time series to the normal distribution. And the function is this one. Basically, you select whatever value, let me call it range 4, whatever name for the variable is QQ norm, and then you will put between parentheses the vector of the data that you want to transform, and then you get from the result, which is a list, only the vector named x. So if we look at this data, you see that the graph is not much dissimilar with respect to what we had before. The difference is the scale. If you look at the scale, there is indeed a change of scale. Let me show you the graph that we had before. This is rain 3. You see that the scale goes from 1000 to 1800. But if you look at the general shape, you see that there is no much difference. There are some differences, of course, but it's very similar. What is changing the scale, and also if you look at the density, you see that it's perfectly Gaussian, perfectly symmetric. And this is a transformation that is called normal quantile transform. It is an empirical non-parametric transformation. I'm not going into the details. It's very powerful. The only problem with this transformation is the inversion. If now I wanted to go back, so to transform back the data to the original distribution, it is quite complicated. So this is why this is not really much used. And I didn't introduce it to you when we discussed stochastic processes. Instead, I introduced to you the log-normal transformation, taking the logarithm. The reason is that the logarithm is very simple to invert. This transformation is very simple to make, but then inverting it is a bit complicated, and you need graphical techniques. It's a bit, but still, given that in this case we don't need to invert it, this is quite useful. And I'm not going into the details because it's very simple, but it takes a bit to explain. So let's just take it for granted. Yeah, please.
I'm getting an error saying I could not find the function 2.1.
Did you check the spelling? You should find it. What about the others? Did you find it?
Yes.
Okay, so I think the problem is the spelling. Couldn't find the function QQ norm. It's double Q. Did you put like double Q? Yeah. Let me check. Where is it there? But there is a plus here, which is no, it's just trying to make it again. No, try to repeat. Because there is a plus that I don't understand. Okay, perfect. Because it was, you joined two instructions on the same line. Okay, now, what should we do? You remember that we should divide this data. We should subtract from this data the average and divide by the standard deviation. And, you know, in order to standardize the data, this is what we have to do for computing the SPI. So basically, I said the data, if we call our data PT, I said the SPI computed at time t is equal to Pt minus the average of P divided by the standard deviation of P. This is the SPI. After you normalize the data, after you make them Gaussian, this is what you have to do to compute the SPI. But in this case, we don't need to do this. Why is that? Because our transformation, the transformation that we just applied, by definition, brings the data to zero average and unit standard deviation. Let's check it. If you compute the average of range 4, it's 0. And the standard deviation of range 4, it's 1 already, very close to 1. Of course, there is an approximation, a numerical approximation, but it's very close. And this is because of the transformation that we applied. It's already embedded in it. So the transformation not only makes the data Gaussian, but makes them distributed according to Gaussian distribution with mean 0 and standard deviation 1. So we don't need to do anything. So what is the result? The result is that our data plot, which is not there anymore, it's already a plot of the SPI. It's already a plot of the SPI for the yearly data. So for each year, we computed already here the SPI. And what you see is that, it's varying from basically from -2 to +2, with some exceptions. And you may remember the values for the SPI which identify critical situations. And of course, you can recognize here that the most critical here was this one in terms of lower precipitation. It was quite exceptional. And then there was one year characterized by high precipitation. Of course, we are interested in the negative values for drought management. So this is the year. So what are the most critical years? This one with an index that is lower than -2, and this one which is close to -2, and again this one which is lower than -2. Still, they are not very critical situation because you may remember that it's a value of -3, which is a bit concerning, and we don't get any value that is really, the minimum here is, sorry, I can close this one, the minimum is -257. And if we look at the SPI, I'm still missing the web page on drought management on the website. Sorry for that. I completed the human impact, but I didn't complete. So I just clicked on the first link. And here you see a description of how it is computed, and the description is what we did. He's assuming another distribution, and you see here the critical values. And no, it's not critical, sorry. This is a correspondence between probabilities, and this is a graph that is similar to what we got for annual values. Of course, it's another time series. And let me see if we get a table with the critical values. I could say no. Okay, let me look for another, because I was looking for a table. This is in Italian indeed, and I'm not sure. No. 1 second. Meteorological Organization. This is quite a reliable source. Let me see if we get something interesting here. Here. So basically what you see here is that, it becomes up to -1 is near normal, and then it's -2 and less that is extremely dry. So I think we got 1 year in our series that was a about extremely dry, which is this one. Okay, this is for the annual data. Now the next step is let's pass to the monthly data. The algorithm is the same. It's the same sequence of instructions. The only difference is in the indexes that now, you know, for the years, the vector of indexes was given by one block of ones and one block of two, one block of three. Now we have for each month to identify an index for each month, which means the first month should have index 1, the second month should have index 2, up to the last month, which is number 1200, because 100 year times 12 months. So if you don't have any question, I would propose to move forward with the computation at monthly time scale, and then I leave to you the computation at weekly time scale, which is the same more or less, and it's the same algorithm. What are we expecting in the month? First of all, you know, the comparison should be made at monthly time scale, so we shouldn't compare each of the monthly values with an overall average. We should compare the values of January with the average of January, and so forth. So there is indeed some change to make in the algorithm here with respect to the annual values. But first, let's compute the monthly rainfall. This is our starting point. We need the series of the monthly rainfall. Okay, so let's go back to the R window, and we have to remember here that what are the names of our variables, and basically we need to go back to rain 2, I think. Yeah, we need to go back to this, because this is the vector of the hourly rainfall, while rain 3 was already the vector of the yearly rainfall. So we have to go back to rain 2, and rain 2 should be aggregated to monthly values. So first of all, I need to build the vector of the indexes. So let me go back to the fourth cycle that I used to build the vector of the indexes, which is, I think, this one. Yeah. First of all, I should define another. I think I can use, again, PR1, yeah. So let me overwrite it, and then let me get the full cycle. But in this case, I should go up to 1200. And then this is the instruction. This is a bit tricky because the months have different length. So we need to think at it a little bit, because it's not so easy. And I think what is needed here is probably we need to create 1 year plus 12, yeah. I have to start from scratch. So let me start from here 1 equal to 0. I think the best solution is to first create a vector of indexes for 1 year. So let me make it. I do it for the first month, and then I tell you. So this is for January. So my objective now is to create the vector of indexes for the first year. And what I have to do is, given that for the first year, the month of January is the first month, I have to build a vector which contains the index 1, which refers to the January of the first year. How many times? 24 times 31. And then I move forward with the index 2, which is February of the first year, up to December. I think I have to do it manually because the number of days in the month, I need to, there is no analytical relationship, so I need to make it manually for the first year. So I move forward, repeat 2, 24 times 28. And then repeat 3, 24 times 31st. I hope I don't get in trouble when I get to the end of the line. We will see. Repeat 4, 24 times 30. Repeat 5, 24 times 31. Repeat 6, 24 times 30. Repeat 7, 24 times 31. Repeat 8, 24 times 31. Repeat 9. Now I have a visualization problem here.